There we go. So, welcome back, guys. Hope you had a great Easter holiday and a weekend, except that all of us are stuck at home, so it's not the usual Easter plans, but at least you probably got to do some more sleeping than the usual. Where we left off last class was that we started seeing combined distributions and operations with them. I don't know if you finally understood what was happening on exercise 4. I uploaded some materials, although I did upload them too late. So did you guys understand the general idea of this thing? Can you guys hear me? You cannot hear me much, or did you not understand the idea? Oh, okay, sure. Let me make a quick recap of exercise 4. So we had two distributions. I believe it was x and y. So x and y, they are both distributed as a uniform distribution from 0 to 1. And they are independent in between them. Independent and identically distributed. Now, the distribution for x and the distribution for y plots like this, right? From 0 to 1, it's a uniform. So you have the same probability for every single point, right? Now, if you have two of these, so this one as well, let's say this is x, this is y, and then you sum them in order to get x plus y equals to w, then w will look something like this, where this is 0. The maximum value should be 1 plus 1, 2. And the most reoccurring value should be 1. This is w. And now in order to calculate the probabilities, and in order to calculate, so probabilities generally are just areas. So it's just summing the probability of occurrence up until a certain point. What we calculated last time was the cumulative distribution function. And we had something like this. So our CDF of W we had two tranches, right? We had a tranche that went from 0 to 1, another one that went from 1 to 2, and this one was double integrals, and this one was double integrals, right? Now, why was this case is that when you're calculating probabilities, say instead of W, it was any number. Say it was the number 1. Say you want the probability of X plus Y less than or equal to 1. Now, this is more like the stuff you saw in the stats, right? Then you plot it, or your Cartesian plane. I'm terrible at drawing with a mouse. There you go. You have Y, and you have X. In order to plot it's easier to watch it in terms of Y. So Y less than or equals to 1 minus X. So minus X looks like this. 1 minus X is basically just one step lower, right? So something like this. Right? And you know the lower bounds. So your area of probability will be the meeting, and I probably can do this better by opening up Desmos. I don't know if you guys know Desmos. It's a really cool graphing software. So I'm gonna switch my screen to Desmos. Okay, so this is Desmos. Gonna zoom a little bit more. There we go. So we know some stuff. We know that X has to be greater than 0. X has to be less than 1. Now Y has to be greater than 0. Y has to be less than 1. So we know that there's this square as formed. Now this square is our area of possibilities, right? For X and Y. However, we're looking at another variable. That's the sum of these. So X plus Y has to be less than or equal to 1. You get this area. So this triangle in where X plus Y is less than 1 and also complies with all the other restrictions will be our first W. Now imagine that this is not 1, but it can go from 1 to 2. So our area of possibilities expands. So we have a point up to 1, and then we have to find the other area of possibilities up to 2. where x plus y complies with all the other restrictions. So it's basically the area of two triangles in which their sides are 1, right? Hopefully that made it clearer. I uploaded some material so you guys can review. Another way of thanks. Another way of solving this kind of problems are something called convolution equations. Now I'm not that familiar with convolution equations. However, I also gave you a link on that. So let's return on the exercises. Where's Visual Studio? Let me close the VPN. There you go. Here's Visual Studio. So why does the uniform distribution transform to a triangular one? So think about the possibilities of values whenever you're using a uniform distribution. Most of the cases, when summing two values that go from 0 to 1, you're gonna get something that's uniformly increasing or uniformly decreasing. Now, I think with the I think with the plot at Desmos, it was kind of implied that whenever you increased a little bit of W, the area that you're covering grows. So let's go back to Desmos. Hold on. Oh, there we go. Here it is. Let's go back to Desmos. So the area that we want to look at is the area that's covered with all of the restrictions. So right now, when x plus y is less than 0.23 is this little triangle, right? Now you see that this triangle is growing, linearly because it's a triangle up to 1. And then after 1, instead of growing at the same pace, it's decreasing. Like the values from 0 to 1 increase. From 1 to 2, the area that you're covering, the marginal addition, is lower and lower and lower and lower, right? So the probability of occurrence on the distribution, because we were looking, the triangular one is the partial density distribution instead of the cumulative. The cumulative would have been something like a line. Yeah, like a line. It starts to decrease until it turns into 0, basically, right? So the probability of getting actually 2 is really, really, really small. It's not 0. Actually, 3 blue, 1 brown. I don't know if you guys are familiar. Just released last week a video of interpreting how there is no really something of probability 0 is just that we actually approximate stuff and say that the probability is 0, but probability 0 doesn't exist. Yeah, I hope that was better. And let's go back again once to Visual Studio. Okay, so our last exercises for this, not the tutorial in general, but these questions are a little bit different. Now, they are still operations with distributions. However, we are going to rely on formulas that other people have written, and we're not going to see them as areas. We are more going to see them as actual distributions. Okay? So, our first question is, let C1 and Z2 be two independent standard Gaussian random variables. Now, when it says standard Gaussian random variables, in your mind, just think at a standard normal, okay? A Gaussian is a type of normal that complies with some properties, but for your sake, it's basically standard normal, okay? So think of a regular Z, but two different Z's. Now, what is the expected value of Z1 given that you know Z1 plus Z2? Now, are you guys familiar? I believe this was the last thing you saw with Jesus. Conditional expectations and conditional distributions. Now, you guys have seen these in Econometrics 1. So it's not something new. However, what I do want to review with you guys is the formulas that you have to apply in this case. So when you have this kind of distributions, you get something called a joint distribution. So a joint distribution, for starters, you no longer have something that looks like f of x, right? Before you had f of x, or let's say f of x. And it was really straightforward doing an f of x. Your mu, if f of x was a normal distribution, and I forgot how to write the normal squiggle. Where's the squiggle? I don't know. Oh, there it is. Sim. So if you have an f of x that distributes as a normal distribution with mu and sigma, it was really easy to know what's the mean and what's the variance. It's already on the data in the values that they give you, right? However, when you have something like this, h of y given x, this is no, and let's assume that x and y are normal distributions. This is not a normal distribution. Okay. Now this has a special type of, I need to color it up. It has a special name. That's a multivariate normal. Okay, I'm not gonna color it just so we fix stuff later. Let's call a multivariate normal. Okay, and a multivariate normal has a in special property. So the expected value of a function like this, so the expected value of y given x, if both of them are normal, is, well, the actual definition is, as always, an integral. Because remember, when we saw this last time, the definition of an expected value is the sum. So if it was discrete, is the sum of values times the probability of occurrence of each one of them. Now, since we're looking at continuous distributions, instead of a sum, we have an integral, right? It's the same thing as to the actual definition for these. So from minus infinite to infinite, from minus infinite to infinite. Of what? Of our values. So of y, because the values of y are the ones we're looking at, times the probability of occurrence. And the probability of occurrence is h of y given x. And b of y, right? Uh, okay. I used the wrong. Okay. So instead of that, we have something that we can actually, hopefully, remember. That is the solution of that equation, given that we are working with two normal distributions. Now that equation is mu of y. So our expected value of y given x is the actual mean of y, however, with a certain deviation. Now that deviation is rho, and rho will be the correlation in between x and y times let's just do it the normal way, times the sigma of y divided by sigma of x. All of this multiplied by the difference in between x, and I'm not using mean, this is actually a variable, minus mu of x. Okay, it's basically the the actual mean of the main variable that you're evaluating with the deviation of how much is x deviated from its mean times the how different the shape of the curve is. So that's what this rho times sigma y divided by sigma x is telling you. Okay, so we're going to apply this formula several times today. Right, so let's go back to this exercise. So instead of y and x, we have something that's AW, we like to call variables W, that's C1 plus C2. Okay, so our exercise is to calculate the expected value of C1 given W, right? And this way we can apply our formulas. Now, before we calculate this, what is the expected value of W? Now you guys can solve this, right? What is the expected value of W? Correct. The expected value of Z1 and the expected value of Z2. Now, in order to make our lives easier, let's say that the the mean for Z1 is mu1, the mean for Z2 is mu2, the the variance of, well, the standard deviation of Z1 is sigma 1, and the standard deviation of Z2 is sigma 2. Okay, so this would be mu1 plus mu2. Great. Now, variance. What is the variance of C1 plus C2? What is the variance of W? And since it's II, that's the covariance of those two variables. Mm-hmm. Correct. Correct. Mm-hmm. Right. Now, just let me check a sec if the original equation it's with sigma squareds. No, it's just standard deviation. Okay, that's good. All right. So we can replace our values then. So instead of mu of y, our y is Z1. So we're gonna write mu 1. And the deviation, it's plus our rho in between z1, or rho in between 1 and 1 plus 2, basically. Is multiplied by sigma of 1 divided, and this is not divided, this one is divided by sigma of 1 plus 2 question popped up. Yes, correct. So divided by sigma of 1 plus 2, all of that multiplied by the distribution, so I'm going to write it like this, of Z1 W, since it's easier, for W in small, minus the mu of both of them, mu of 1 plus 2. Okay, so now we just have to plug in our answers, right? And we have to remember something. Now I'm gonna go back to that later. Before calculating this, we need to know what is this rho. From theory, Sebastian. Well, you can actually get it if you replace instead of that y and instead of the h, you actually truncate it and then you plug in the normal distribution, you'll get that. So we need to calculate rho. So rho in between 1 and 1 plus this being z1 and z1 plus 2, z1 plus z2, is the usual formula of a correlation, right? So let me quickly search up how to do a fraction. It's frac. Yeah. So on the top we have the correlation. So C of C1 and Z1 plus divided by sigma 1 times sigma 1, sigma 2, right? Here. That's how we get correlations, correct? Now, since, let me do a little zoom over here. A way to operate correlations when you have pluses and minuses on one of the sides is that you can look at it as two pieces, right? You can look at it as correlation in between C1 and C1 plus the correlation plus the covariance, I mean, of C1 and C2. Now, we know that the covariance in between C1 and C2 is 0, correct. And the covariance in between C1 and C1 is the variance of C1. Great. So we can get this better. And let's do another fraction. So on the top, we only have the variance of C1 right now. So sigma 1 squared. And on the bottom, we have sigma 1 and the square root of the thing that we already calculated. Right? Right? So we can do something, correct? We can, this C1, this sigma 1 squared divided by this sigma 1 will leave us with just sigma 1 on top, right? We can remove this sigma 1 and we can remove the square. Now, so far, we've been using just mu's and sigma. However, the actual thing is that we know these values, right? Because the exercise told us that we are using standard normal distribution. And we know what's the mu of a standard normal, and we know what's the variance of a standard normal. Correct? What's the mu of a standard normal and what's the variance of a standard normal? 0 and 1. So our fraction will turn into sigma of 1 is 1. Sigma of 1, variance of 1 is 1. Variance of 2 is 2. So divided by square root of 2. And we can use regular math and multiply it by square root of 2 that divided by square root of 2. So this looks into slash frac square root of 2 divided by 2. So now that we have this, let's go back to this thing, our expected value. And now we can replace the stuff, right? Mu of 1 is 0. Rho of these we just calculated is square root of 2 divided by 2. Sigma 1 is 1. Sigma of 1 plus 2 is 1 plus 1, so 2, but square root since it's sigma, right? W we leave as W. Mu of 1 plus 2 is 2. No, it's 0. So 0 plus 0 is 0. So now we have square root of 2 times square root of 2, that makes 2, divided by 2, that makes 1. I've missed something. I missed a 2 somewhere. I'm missing a divided by 2 somewhere. Oh, this one. Yeah, I missed this one. So sigma of 1 plus 2 is it's a square root of 2, right? So this one is divided by square root of 2. And now we have w divided by 2. That's our expected value of z1 given w. Mm-hmm. It's like this. Yeah, it's better. Okay. Any questions? No? Okay. So the next question is quite similar. Okay, it says let x and y be two independent Gaussian random variables. This is no longer standard normals. So it looks something like this. What is the expected value of x given x plus y? Now this is really similar, right? We can actually jump into the solution, right? So let me quickly grab this one. And let's replace this stuff. Instead of, no, this is much easier. Instead of, I can grab this one, and this is going to be easier. Okay, here it's x divided by, well, not divided, given x plus y in caps. So this is mu of x, rho of sigma x divided by sigma of x plus y, x plus y minus mu of x plus y. Mm-hmm. Okay, since we know that they are independent, the same thing applies, right? The covariance in between x and y is 0. The correlation in between x and y is 0. However, the correlation in between x and x plus y is not 0. It's something really similar to what we had over here. It's sigma of x divided by the squared sum, the root of the square sum of the two sigmas. So let's just go on and replace values. Mu of x, we know that the mu is 0. Rho, we know the values. We have to write it out. It's sigma of x, which is a, divided by the square root of the sigma of x squared. Before the square root, we had something else. A square root of a. The square root of a times the square root of the sum of the squares. So a to the power of 2 plus b to the power of 2. That's our rho. I messed something up. Oh, a is sigma. Okay. So it's not to the power of 2. Yeah. Sigma of x is square root of a. And this is with the squiggle brackets. Sigma of x plus y, we just wrote. Yes. Plus y stays the same. Mu of x plus y is 0. There we go. So this square root of a and this square root of a go away. This square root of a plus b goes with this square root of a plus b and turns into just a plus b. So our final answer is that this thing turns into fraction a divided by a plus b times our y. Right? So good so far? All good, guys? I'm gonna take this moment to take attendance. Álvaro Adriansen. Sebastián Guerrero. Sebastián Aybar, I mean. Mauricio Barrios. No, Mauricio. Y Elena Borja. A ver, es Mauricio. No, y Elena. Estuardo Chalán. Sebastián Collantes. Jean-Pierre. Xiomi García. No, Xiomi. Roy Portilla. Roy. Fernando Ruiz de la Cruz. Sebastián Salinas. Giuseppe Valeriani. Andrés Vilcahuamán. Marcelo Villar. Awesome. Okay, so I'm gonna leave number 7 as a little quiz for you for right now. And for those who didn't attend the first 2 classes, or maybe didn't hear Jesus on the changes we're doing this semester, the participation rate actually has now a much higher weighting. And part of the participation rate is actually being here, answering questions, and doing this kind of surprises stuff. So you guys have to do number 7, and I'm gonna receive the first 3 answers. And you have 10 minutes. Oh, okay, sure. You do have it on Blackboard though, but hope you wanted the time. You do have 5 and 6 and 7. You just don't have the answer to those over there. Did we end up creating the WhatsApp group? I don't know. Did you, Andres? Am I there? Okay. So you can send it through WhatsApp, by the way. It's 999001880. You guys have 7 minutes. I do have you, I believe. I think. So we have one submission, and you do have to solve variance of x and variance of y, which I believe it's A and B. Sebastian, I think it's wrong. Yeah, pretty Let me see where it's wrong. Oh, by the way, you guys don't um one detail that you guys need to note is that part where suppose that x and y are correlated with correlation p, that means that x and y are not independent. So the correlation of x and y is rho. Okay? Remember that. You have 3 minutes more. We have another submission by Jean-Pierre in where he is wrong as well. So is W supposed to be your x minus y or your 2x plus y? Oh, okay, it's all of it. And yeah, it's wrong. I see your issue. So remember that all that you have on the top side is 2x. I mean, it's x minus y. So that x minus y should not ever get deleted. We have another submission of Estuardo. Quite close, though not 100% correct. Okay. Estuardo, you made the same mistake as Jean-Pierre. So, no, there's no half points. Um, x minus y, all of that is conditioned to 2x plus y. Okay, it's the expected value of x minus y given to x plus expected value of y. No, all of x minus y is conditioned to 2x plus y. I'm gonna give you guys 6 additional minutes. Six minutes. Time's running. Because after that, we have to go back and do some more R. Second try by Sebastian. Again, you're closer. Closer. Let's see where you got it wrong. I think it's on the covariance. This is correct. This is... Ah, I see. Where did you get 4? Two times... Yeah, there's no 4. Yeah, Sebastian, you got close. But you got some mistakes calculating variances and covariances. Although the general idea is well done. Let me see Fernando's answer. That part is correct. Fernando, you made a mistake halfway. I think if you fix that, it's going to be good. You got 2 more minutes, guys. Just to give you a heads up on this kind of stuff, last term there were like 2 exercises that looked similar to number 7. One more minute. We got another submission. No, that is not correct. Basically, Fernando, check how you got that 3. And probably stuff will solve it itself. And time's up. So none of you got it? No, I'm not gonna give you guys 10 more. We have to continue with the class. Okay, so nobody got it. I will leave you for home. As well, it will count for the first 3 that submit the correct answer. However, since it's not in class, it will count as half. Okay? Now we're going to go to R. So remember where we left off. Okay, remember where we left off, we saw the types of objects, and I'm going to, as per requested last time by Jean-Pierre, change my thing to white. The white theme I like is Chrome. Let me increase a little bit my font, maybe a little bit more, 16. No, 16 is too much. 14 is fine. Okay. Now we saw that we could do easy operations. We saw how to assign variables. We saw the types of variables, that we have characters. We can do operations with variables. That we have characters, that we have logicals, that we have numeric values. You can check what kind of class that the variable is with the function class. We saw stuff with vectors. We saw how to subset vectors and other type of objects, how to do operations with vectors, how to name objects, some easy function like names in order to name stuff, sum, mean, call means. We saw inequations, subsetting with indexes, with names, operations with vectors, matrices, how to annex different matrices to the right, to the bottom, operations with matrices. We saw factors, order factors, non-order factors, remapping different factors. So data frames, which will be your best friend in R. We saw how to access each different column, how the objects are structured, how to subset them. And we saw lists. And remember, lists could contain basically anything inside of them. Okay, that was last class that we saw an introduction to R. And now we're going to see statements and also functions. So let's see those stuff. Let's say that we have the x is minus 5. We can write as an if statement. Now, an if statement is if, parenthesis, a condition that has to yield you true or false, brackets, and whatever is inside the bracket will happen if the condition is true. So right now, x is 5. If x is greater than 0, so right now x is greater than 0, 5 is greater than 0, whatever is inside of this will happen. So this is print positive number. So if I run this statement, it'll print positive number. Now if x is minus 1 instead, minus 1 greater than 0 yields false. That means whenever I run this, nothing will happen. However, if I run non-negative number. This is the other way of writing if statements. If you want something that's not complex, you can write it on one line. If you have something that has more than one line or it's more complex, then you use the bracketing structure. Okay? So right now, if x is 5, x is greater than 0, yes, true. Print non-negative number, it'll print non-negative number. If I run if my condition something, I can use also an else statement. So the else statement is when it's true, it'll run what's inside of here. When it's false, so the else, it'll run this thing. So for 5, it's non-negative. If it's -1, it'll run negative number. I can write the same thing in a bracketing structure. So I have -1 right now. -1 will yield us negative number. 5 will give us positive number. However, my current structure doesn't account for zero values. 0 is not positive nor negative, right? That means that I need to modify my if statement. If x is less than 0, I want it to print negative number. If x is greater than 0, I want it to print positive number. Else, so basically if x is equals to 0, I want it to print 0. Now notice that instead of just writing else, I wrote else if. Now else if introduces a new if statement to the equation. Okay? And all of these are correctly closed. This one closes this one. This one opens. This one closes. This one opens. This one closes. Okay? So logical operators. Now I went ahead and told you guys that whatever is greater than 0 will be considered true on R. So check out this vector. True, false, 0, 6. However, look at my environment. My environment saved that as a numerical of 1006. Now instead, false, true will be a logical vector. This does not mean that we cannot use this x vector in order to do logical operations. Now, this is the not operator. This exclamation point is the not operator. Whatever is false will turn to true. Whatever is true, it'll turn to false. So right now, x is true, false, 0 is false, 6 is true. So it'll turn it into false, true, true, false. Let's check it out. False, true, true, false. Now this ampersand is the AND operator. Whenever you have true and true, it'll yield true. All the other cases, it'll be false. So it should yield true for the last one and just the last one. That's correct. Before checking this one out, let's see the OR operator. Now the OR operator will give us true whenever at least one of them is true. So all the ones except where it's 0 and false. So false and false. Now these ones where it has two of the same operator, they are rarely used, but it'll only give you the first result. So instead of getting the whole vector, I'm just getting the first one. Okay? So I'm just getting this one. These are rarely used. I actually have never used them to anything practical. So far, so good? Roy, I will check your answer later. Pay attention to R right now. Okay, let's go with for statements. So for statements will basically be your easy to do loop. Now looping means doing the same thing over and over again for a different set of values. Now for is not that much used in R because you have better alternatives in order to do vectorized loops. And we're going probably, no, I don't think this class, but probably next class, we'll see different kind of loops. And I'm also going to upload some material for you to review. So let's turn x into a vector, 2, 5, etc. And we're going to save a variable where it's count, and we're going to reset it to 0. Now for is very similar to the if statement. For in whatever variable you want it to change in between the loop, and you give it a set of values. Now the set of values right now is all the values of x. That means in the first iteration, val will be 2. In the second one, it'll be 5. In the next one, 3. Then 9, then 8, then 11, then 6. Now the first thing I want is to print me the value. So to show me just whatever value it's working with. After that, I'm introducing an if statement. If the value modulus 2, now remember what was modulus? It was like the residual value, right? So the residual value of dividing by 2 is equal to 0. Double equals, remember, is whenever you want to compare something. So whenever this happens, then it means that the number is even. So if my number is even, I want my count to increase by 1. Now, how many even numbers do we have in X? We have 2, we have 8, and we have 6. So 3 values. So if I run my loop and I print how much count has is 3. We have 3 even values, and we got 3. There is a different way of doing this. Now, instead of looping through every value that x has, we could have done, let's reset count, could have done a vector that's 1, 2, 3, all the way to how many elements x has. And we could have subset x in that space of element. And it'll be exactly the same. Now, just to vary a little bit, since I'm not doing something really fancy over here, I'm putting the if statement in one line. Just because you could do either way. I always prefer to do it in the bracketing way, but you can do it if it's just one line in this way. So let's check it out if we get the same thing, and we do. Okay, let's go to the while statement. Now the difference in between for and while is that for will loop for how many variables you give it, how many values you give it. While will only stop if it reaches a certain condition. That that's why if you're programming a while statement, you need to be careful that that stopping condition will happen. So let's say that we have I equals to 1. And while I is less than 6, print I and increase I by 1. So I will be 1, then I'll be 2, 3, 6, etc. Until I is um, equals to 6 or greater than 6, then this statement will stop. So it's 1, then 2, then 3, then 4, then 5, then it turns to 6. It evaluates the condition and it no longer runs. Okay? So far, so good? Okay. Now, break is something that's kind of useful whenever you have a for loop that's really big and you want it to stop, just like a while statement. You want it to stop at a certain point. So let's say that our vector is a numeric of 1 through 5, and we want it to stop whenever it reaches 3. So we're going to print the value, and we're going to program in an if statement that whenever the value is 3, it'll break. That means it'll no longer run after this point. 1, 2, 3, value is equal to 3. Yes, true. Break, and it no longer runs. So we're not wasting memory. Okay. Next is kind of similar. However, it'll skip everything that's after the next just in that loop iteration. So again, we have a vector of 1 through 5. And whenever it's 3, we want to skip that. So 1 is going to print. 2 is going to print. 3, it'll evaluate this thing. It'll say next. And then it'll go to 4. It will no longer run whatever is after that. It'll go to 4, it'll print 4, it'll go to 5, it'll print 5. So it skipped 3. 1 through 5 is just telling me I want a vector of 1, 2, 3, 4, 5. Let's say we have a vector of 1 through 50. And whenever it's an even number, we want to skip it. So we are only going to print odd numbers. Right? So these are the odd numbers. We have other less known statements. One is repeat. Now, repeat, what it does is it'll repeat the same statement like a while statement, but it doesn't have a stop. You need to incorporate a break for it to stop, or else it'll run to infinity. Okay? So right now I wanted to print my value, increase my value by 1, and if my value is 1,000, stop. So this will run until infinity, except if I have a break over here. And then it stopped. So if you check the value of x, right now is 1,000, so it doesn't continue. If I do 10,000, it'll go all the way until x turns into 10,000. Okay? So you have to be careful if you're using a repeat statement that you incorporate a break that can actually happen. Switch. Now, switch is really similar to, to the function choose in Excel. So switch tells me that I have a set of values that it can choose, and I can give it an index or I can give it a name. Okay, so it can I if I say switch in between one or two and get the first one, it'll give me one. If I say switch the second object that my switch statement has, and I have the object one and the object two, it'll give me two. If I have them by name, I can either do by index, like we did before, or by name. And that's basically it with switch. It's quick and easy choosing between my set of values. Now, if else is quite similar to doing an if and an else statement, except that it works exactly like the function if in Excel. Is there a difference between using the brackets or not? Yes. So the brackets tells R that you're using a complex object. So basically an object with much more structure. The difference in between these is that right now I just put it with a character inside. However, inside brackets, I can put a whole function. I can put a whole different lines. So I can put 50 lines of code over here, and in this one I can just put one object. That's the difference basically. So if else works exactly like the if function in Excel. So the if function in Excel was if um, uh, log logical condition, yes value, no value, right? So true value, false value. That's the if function in Excel. If else in R works exactly the same. So we have the condition on the first argument, the true value and the false value. The difference is in Excel, you can use vectors. So whenever my value is even, I want it to say even. Whenever it's odd, I want it to say odd. Since I'm giving it a vector, it'll do this for every single item in my vector. Odd, odd, even, odd. Pretty easy, right? So the last thing we're going to see, and I'm gonna give you, not sure if one or two homeworks, but in order to give you chances for extra points. So in order to create a function in R, you create a structure just like the statements that we saw with brackets. And whatever you put inside that function will run whenever you call that function. So remember that functions always have parentheses, okay? So right now we haven't given it any argument. That means that we do not have to put anything in the parentheses to run it. So my functions will do, as I stated, it'll print hello. We can give it arguments. My function name takes a name, and whatever I want it to do is paste hello with that name. Paste is basically like concatenate. So if I write my function name David, it'll say hello David. If I write my function name Andres, it'll say hello Andres, and so on. Now, if I want my function to be more complex, if I want my function to be more complex, I can tell it that I have a default value. So that means that whenever I don't give it any argument, it will use that one. Okay, so inside right now it's the same as before. If I don't give it any argument, it'll say hello David. If I do give it a name, it'll say hello Sebas. A function that we use quite usually in Excel is sum product. Now we can recreate it in R really similar. We give it a vector of x and a vector of y, and we say that we want the sum of x times y. We have an object, a vector, a that goes 1 through 5, and b that it's 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5. And we do sum product, we get the sum product. Now, we do have certain functions in order to check what's going on inside a function. The first one is body. So body will give me whatever it is that the function is doing. So whatever is inside the brackets. Formals will tell me about the arguments. So the arguments are x and y. Now, the difference is we didn't give any default values over here. We did with my function name 2. My function name 2 had the default value of name being David. So it'll show me that name, the default value is David. Environment tells me where it's allocated in the memory. That is useful because checking environment, what we are seeing right now is the global environment. However, if I click on this, we have a lot of more environments. Okay, so global environment is the one that you usually see, but they are hidden environments, depending on which packages you have loaded and which environments you can create, because you can create environments by yourselves. Let's say I load base. Base is always loaded, by the way. And I want to check the environment of the function called abbreviate from the package base. Now, these two double dots tells me that I want the function abbreviate from the package base. So if I have more than one function called abbreviate, I'm specifying that I want the one from the package base. So this one is on another environment. Is on the environment of the namespace base. And if we go to package base, we will see that I have a lot of stuff inside of here. I have everything that's loaded by default in R. So base is the base package of R. So all of this I can call without adding something new. So this is basically most of the usual functions that you call in R, and you don't have to use library for it. In other functions that we'll see, and we'll see how to apply packages. And packages you do have to load like this, like library and the name of the package. Okay, let's go back to the global environment. Environments are for storing functions. Environments are for storing everything. So as you can see, our global environment is storing values, is storing functions, and we can also store objects. Say X is empty cars. So empty cars is now a data frame and it's saved at our global environment. Okay. Now, other useful things that you can do with other useful things that you can do with functions is to give your user more information. Say if we want to create a square root function, you just say that we need an argument x, and if you don't give us the x, we don't want to run the function. Okay, so if missing x, so if x has no value, you want to input a warning. Let's say argument x is missing. Now, a warning doesn't stop the function. It'll still run. However, it gives the user information. So if we run it without any information, it'll give us an error. And in addition, it'll give us the warning that we wrote. Warning, argument x is missing. What happens if you overlap any default function? You will run probably the newest function on the global environment. So usually the global environment has priority over any other environment. So when you don't want to create a function with the same name as the usual function. Now remember that R is capital aware and case sensitive. That means that sqroot is not the same as sqroot. Okay, so that gives you a little bit more leeway when you're writing stuff. Okay, we can also do another statement called stop. So while warning still lets the function run. However, a stop will stop the function from running, and you can make it give the user a message. So what we're saying here is that if any of x is less than 0, that means it'll evaluate x is less than 0, and if any of them is false, it'll input a true statement. I mean, if any of it is true, it'll input a true statement. Just like any, there's all. So any is for just one. So see, false, true. You're giving true because there's at least one true. Or if I run all, this will give me false. I need all of them to be true, so I get true. Okay? Let's update our square root function. And if I have any negative value, it won't run. It'll error out, and my stop message will appear over here. Now, if I change this, if I make this 6, my function runs. Okay? Now, since we're finishing up in a bit, I'm gonna leave you more homework. So remember the exercise. The first exercise that we did on last class. So the hashtag is for commenting, by the way. So we had this exercise last time. The player tosses a die once only. The payoff is $1 for each dot on the upturned face. Assuming a fair die, at what level should you set the ticket price for this game? So I want you guys to make something like this. You might need more than one function for this. So I want you guys to create a function called roll. Function roll has to have as an argument nothing and has to give me a value in between. Oh no, this is much better. I want a max value over here. A value in between 1 and the max value. A random. A random value in between all of these. Okay, so maybe the first time it will give me 2. If my max value is 1, then it can only give me 1, right? If my max value is 2, then sometimes I'll get 1, sometimes I'll get 2, sometimes I get 1, sometimes I get 2. Okay? Then I want you guys to create a function called fair price. This function should have the argument rolls, and it should give me the fair price, even, and I'm going to get ahead of you and tell you guys that you probably want max value over here as well. They'll give you the fair price given how many rolls you want to do. And taking into account the and taking into account the max value your die can roll. Mm-hmm. Should be easy, right? Now we have like 5 more minutes. If one of you can can write these 2 functions in less than 5 minutes, you get double the usual. But if I'm gonna leave it for home for the rest of you, and it's going to have normal score, not like the one that has half. Okay, you guys agree? Oh sure, I am. I am going to upload this. Okay, I joined. The code could be sent through anywhere, basically. You can send it by email. You can send it through WhatsApp. Anywhere where I can copy and paste it or just download it. But it has to run, right? Now, a function that can be useful for you guys to use, it's sample. Okay? Now, remember, and I'm not going to tell you much more. Just remember that whenever you want to know more about a function, you can write a question mark and the name of the function, and it'll give you the help page for that function. Okay, so useful. Okay, going to upload everything that we did today, and that's it. You can ask me questions. Prefer I won't tell you the answer. I can guide you to towards if you're going through the right or the wrong path. But yeah, this should be good practice. Um, I will be giving you more assignments like this, and it'll get more complex whenever we're advancing. When's the last day to send it? Let's make it Max Friday. So assignment Max on Friday night. No, Friday morning before class. How many obtain the points? Everyone that sends it correctly. And I do consider so the way I grade stuff whenever it's somewhat of an open thing is that I reward creativity and investigation. So if you make it better, you'll probably be better off than whoever gave it the minimum required thing. So if your function is faster and it's better, and maybe you even do an output, maybe you do a report, maybe you test, you replicates and stuff, it'll be better, right? I'm not going to answer that, Roy. You'll know your participation grade whenever the grade comes. Because I can say 50 points, and I can maybe not tell you out of how much it is. So the way the participation grade works, it's not a something that's additive to your exams. It's a part. Estuardo, tell me.
Gonzalo, I have a question. You can At the middle of the semester, you can say our participation note so we can improve or
Sure.
see how we're doing. Okay.
Yep.
Thank you.
So yeah. Does any one of you have an additional question? Okay, I guess not. Then class dismissed. See you next Wednesday, guys.